Hi, my name is Blake Hewgill, and this is my talk on the development of a modular wearable sensing device for stress estimation. I need to thank both my advisors, Jeff Frolick of the Sensor Network and Wireless Lab, as well as Ryan McGinnis of the MSense Group, as well as the Vermont Space Grant Consortium for funding my efforts. Now, before we can talk about stress and stress estimation techniques, we need to formally define what stress actually is. Now, according to Merriam-Webster Dictionary, stress occurs when the demands that are being placed upon a person tax or exceed available resources as appraised by the individual involved. There are a few different types of stress that we need to be able to distinguish between. The first division that we'll talk about is physical versus mental stress. Physical stress occurs as the body responds to external stressors like during a workout or other exercise. Mental stress is how an individual perceives the world around them and how they deal with events that happen to them. The other distinction we need to make is chronic versus acute stress. Chronic stress is stress that's experienced over a long period of time, whereas acute stress is the short-term response to an external stressor. For the purposes of this video, we'll only be interested in mental stress, though we will be considering both chronic and acute stressors. We won't be distinguishing between these two. There are many severe consequences of stress. These include increased absenteeism in the workplace, which is where an employee is present at their job, but the level of effort they're putting in is far below their standard. There are also risks of increased psychological as well as physiological disorders. These can include weight gain, heart disease, sleep problems, anxiety and depression, as well as many others. In some workplace environments, high stress levels have been proven to correlate with increased risk of workplace accident. Stress can also impact both short and long-term memory, and in 2019, the American Institute of Stress estimated that stress cost the U.S. industry $300 billion that year. Now, quantification of stress is not a new topic, but to date, stress is usually estimated using self-estimation methods. One of these methods, and most widely used in clinic environments, is the Perceived Stress Scale, introduced by Cohen in 1983. This test consists of 10 self-evaluation questions ranging on a scale from 0 to 4. Now, at the end of the estimation, your score is added up, and there are 3 outcome categories. There's not stressed, there is some stress, and there's extreme stress. Additionally, the perceived stress scale suffers from limited time resolution, as it only considers the last month. There is no increased granularity. Finally, in order to actually fill out a perceived stress scale estimation, workplace actors, or employees, need to stop what they're doing, sit down, and actually fill out one of these evaluations. Most importantly, because the perceived stress scale asks individuals about their personal feelings, there's an incredible level of subjectivity involved in the estimation. This is the main point that we in this work attempt to address. We propose the development of a wearable garment called the Wearable Integrated Health Monitoring System, which is an open source, multimodal, multi-sensor, low-cost stress estimation. The proposed system includes a 3-lead ECG, skin temperature sensors, a respiration sensor, moisture sensors, pulse oximetry measurement, heads-up display, as well as a custom data consolidation board and onboard processing and battery. In order to perform the data logging present on the WIMS system, as well as communicate with our sensors, we settled on the Arduino Mega 2560 microcontroller. This is a hobby-level board with great form support and a 16 MHz clock, compared to the 8 MHz clock present in some smaller sensors. This board also utilizes 5-volt logic and supports both I2C comm support, which is going to be present in most of our sensors here, as well as SPI communications, which is popular for higher speed peripherals such as an SD card, which we'll be using for actually saving off the data. The board provides 16 analog inputs, and in the current configuration of WIMS, we're actually only using 4 of them. Additionally, the Arduino integrated development environment has great pre-built libraries for all of the sensors that we're using. In order to communicate with all of our sensors simultaneously, we created a custom printed circuit board, or PCB, which would allow us to hook up multiple sensors independently of each other. On the digital side, we used the Inter-Integrated Circuit protocol for digital communication. With this protocol, all of the sensors on the bus have unique addresses, and we're able to talk to them individually, even though they're all sitting on the same bus. Now, the problem with this system is even though the I2C protocol is incredibly simple to use, it's very sensitive to long traces, especially cable runs like the ones we're using off-board. So to combat this, we actually segregate each individual bus that every sensor is on in order to keep the capacitance low and prevent the bus from locking up and rendering the communication system inoperative. This board also features onboard power regulation and will take anything from 2.8 volts to 11.8 volts and regulate it to the mix of 5 volts and 3.3 volts used by our sensors for both power and logic. Each one of the ports on the board is configurable, so we can set either 5 volt or 3 volt power levels to that specific sensor, as well as 5 volt or 3.3 volt logic levels. We use Ethernet jacks and phone jacks to allow us to hot swap different sensors on the buses and reconfigure the garment at will. Additionally, a real-time clock timestamps each new dataset as we collect it. Prior literature has indicated that changes in the duration between heartbeats, known as the RR interval, may indicate chronic stress in individuals. In order to monitor the ECG of the subject wearing WIMS, we use a gravity 3-lead heart rate monitor. Now, this is an analog circuit which is based around an instrumentation amplifier, which amplifies the difference in electrical signals across several leads. We use these with 3M red dot disposable electrodes. These electrodes are placed on the lower abdomen as well as on either side of the subject's heart. Prior literature also indicates that sudden drops in pulse oximetry or blood oxygenation levels may indicate stress. In order to monitor these stress levels, we implement a Maxim Max 30102 particle sensor. Now this board features two different wavelengths of LEDs. There is a red LED and an infrared LED. And what we do is we shine these through the skin of the subject, and based on the way that each wavelength scatters, we're able to detect the amount of oxygenation within the blood. Now, this sensor is mounted at the subject's left index finger. Skin surface temperature also plays a role in stress monitoring. Changes in skin surface temperature have been shown to indicate acute stress in individuals. Decreased temperature regulation has been shown to indicate chronic stress. To monitor both skin temperature and ambient temperature, we'll be using thermistors. Thermistors are a passive electrical component which change their electrical resistance based on the temperature they're exposed to. By monitoring the voltage across a thermistor, we'll be able to calculate both the ambient temperature in the room as well as the skin temperature of the subject. This one's probably a no-brainer, but sweat response has been shown to track stress events extremely closely. We can monitor these stress responses with a technique called galvanic skin measurement, which is a measure of the conductivity of the skin, which changes in accordance to sweat response. So in order to monitor this, we created a custom moisture sensing board, which measures the contact resistance between 2 points. Now, it also stands to reason that the location of the galvanic skin monitoring is going to play a part in the results that we see. We standardized on an armpit location. We were also interested in monitoring respiration rate and how breathing changed with different levels of stress. To monitor this, we implemented a Bosch BNO 055 gyroscope at the base of the subject's sternum. Prior art has used accelerometers to estimate respiration, but at this particular location, accelerometry measures were not as repeatable or reliable as the gyroscope proved to be. Finally, a simple micro SD card is used to log data. We use the SPI protocol and store the data in a binary format. By storing in binary, we're able to reduce the data size and increase the speed of the logging. Currently using a 64 GB card, and at current data rates, this will allow us over 3,200 hours of logging before we fill that space. Down there on the right, you'll see a sample of the data structure we've been using. So for our data collections, we had a single subject study, me. The process was that within 1 hour of waking every day, I would put on the WIMS garment, power on the garment, and wear it for at least 10 minutes to allow all of the sensors to come up to temperature. I would fill out a personal stress scale questionnaire to establish my stress levels for the day. I would sit down and I would start the data collection. After 10.5 minutes, the WIMS garment prompted me that data collection was complete, at which point I exported the data, attached the PSS value in the file name, and exported the data to be post-processed. Using MATLAB, we analyzed our signals of interest in both the time and the frequency domains, and extracted features of interest. For the ECG, we extracted the average and maximum heart rate over a 1-minute sliding window. We also measured the minimum. In the frequency spectrum, we examined areas of high frequency and low frequency, as well as the ratio of power between those two areas. We examined these same features in pulse oximetry, but we also looked at the rate of change between each successive beat to determine how quickly the level of blood oxygenation was changing from pulse to pulse. For skin temperature and skin moisture, we examined the maximum and minimum values, as well as monitoring the rates of change over the logging period. Once these features of interest were extracted, we used MATLAB to compute the Pearson correlation coefficients and determine whether these features that we calculated from our data could be shown to correlate with the self-perceived stress value associated with that data set. What we found was that while several of the features did correlate with the self-perceived stress value, the strongest correlation with an R value of 0.75 and a p-value of less than 1,000th was the maximum 1-minute sliding heart rate window. Now, this isn't necessarily to say that the other features completely don't correlate, nor is it to say that a high stress value will always result in a high heart rate. I think more than anything, what we're taking away from this is just how subjective these measurements are. There's been so much prior work showing that these parameters of interest do correlate with stress, and what we're seeing here is that the self-evaluation is so subjective that we might not be seeing that at all. In the short term, moving forward, we definitely have a few goals. The first is adaptive processing. Because the I2C sensors all have unique addresses, it would be easy enough at startup to query all the possible addresses of sensors that we know we may have, and actually change the process flow of the garment based on what sensors we have hooked up to it. Obviously, of course, there is a tremendous amount of opportunity to determine additional features, and I'd also like to move to a stronger, faster microcontroller so we can actually do this processing in real time while the subject is wearing the garment, rather than having to export the data. Finally, I'd love to incorporate wireless data transfer into the garment, just because it's a little bit clunky to be pulling out the micro SD card every time. Thanks very much. I will answer questions as best I can in a timely manner. Please don't hesitate to reach out.